Okay, so welcome back. All right, so we needed to finish up a few cases um, for faceplane portraits from yesterday's discussion. So yesterday we had covered the two real roots case, the two complex roots case, and part of the case when you had one real double root. Namely, we'd cover the case when it's a multiple of the identity. So we are still in our mega case 3, and we're in the subcase when A is not equal to some multiple of the identity. Okay. Now, in this case, a generic A having having an eigenvalue that's a double root might look like this, right? Or just our generic matrix. Now, unlike in the complex case, A21 and A12 either of those can be 0. Okay, so because of this, there's going to be a rotation component for these pictures, but because A21 can be 0, we can't just use A21. We have to incorporate a test, or we have to use a test that incorporates both of those entries, possibly. Okay, so on account of this, if A21, so we're going to, our cases are going to break up in the following way. A21 minus A12, if that is less than 0, this implies clockwise motion. And A21 minus A12 greater than 0 implies counterclockwise motion. That's how these cases are going to split up. You can remember this if you like. Again, we've oriented it in such a way. We could have used the negative of these things if we really wanted to, but I've oriented it in such a way that it matches with the right-hand rule, just like our last test for these things. Okay? All right. And so what are the cases? Remember, our cases, lambda is equal to, so our eigenvalue, lambda is equal to mu, we'll say, right? And this is a double root of the characteristic polynomial for our matrix A. Well, there are 3 possibilities for what kind of real number mu is, right? This is just trichotomy. So there's the following 6 cases. All right. So the first case is mu equals 0, and A21 minus A12 is positive. I think they do negative first. Maybe I should do that so that I'm in keeping with the notes. So yeah, A21 minus A12 is negative. The second case is mu equals 0, but A21 minus A12 is positive. The third case is mu is negative, and A21 minus A12 is negative. The fourth case is mu is negative, and A21 minus A12 is positive. The last 2 cases, as you might have guessed, mu positive, A21 minus A12 negative. And lastly, the last case, mu positive, and A21 minus A12 is also positive. Okay. All right. So let's see what these cases look like. Okay, so the first two cases, I will put the eigensolution orbits, or the eigensolution trajectories, in blue here. Everything else will be in black, if I can get my blue pens to work. Okay, so here's my eigensolution. Here's the origin. Same thing here. Okay. What do other trajectories look like here? Well, we'll say that this is the clockwise case. So the clockwise case, I have trajectories that are also lines here that are parallel to this, but the direction indicated is in the upper plane is to the right, and in the lower plane my trajectories are also pieces of lines, but my motion indicated is to the left. So this is clockwise. Shear. Then in the other case, I have a counterclockwise shear. So in the upper plane, I have motion to the left, and in the lower plane, I have motion to the right. This is a counterclockwise shear. Okay. So these are both shears, and this is both when mu is equal to 0. Okay, so in that case, we get shears. You can see why it's called a shear, because if you take both of these things, you think about sliding them in this direction. That's what these are doing. So it is a shearing motion that's going on here. That's what describes these trajectories. Okay. All right, so let's see the next two cases. So now I'm going to have an eigensolution that's not just the horizontal line y equals 0, right? So it's not just 0 here. It's not just a constant thing. What is the vector that determines this line look like? It's still a line, okay, but so it's still a line solution. But rather than getting two of them, like I do in the case of having two real eigenvalues, I only get one here because I technically only have one eigenvalue, right? Okay. So my line solutions only get one of. So because of that, they don't block off the plane in the same way, right? In fact, it only splits the plane into two pieces. Now here's my origin. Now let's say that we are in the mu less than 0 case. So then I have motion towards the origin along my line solution, right? The eigensolution. The same thing is going to be true over here, right? Because mu is negative. Okay, so in both cases it's motion towards the origin, but in this case, this is going to be the clockwise case. I have clockwise motion along trajectories like this towards the origin. So here's another one. All right, here's maybe another one. And here's one more. Okay. So this is a clockwise. This is a clockwise twist sink, is what it's called. This is going to be a counterclockwise twist sink. Okay, so what that motion looks like is this. Okay, and then, nope, I didn't connect it. This is a counterclockwise twist sync. Just so I don't have to write this a bunch, clockwise would mean A21 minus A12 is negative, and counterclockwise means that A21 minus A12 is positive. So that condition on being clockwise or counterclockwise, that's the same test regardless. Okay. All right. So these are called twist sinks. Sinks because they're going towards the origin, but twists because, well, look at the motion, right? It looks like this thing. So now, why does it look like this, and like why doesn't it look like this in the original case? In the original case, I had another eigensolution, right? Another line solution like this that blocked off the plane and prevented stuff like this from happening. Okay. All right. So then let's see the last two cases. So this is the case when mu is greater than 0. What does this look like? Well, again, I have eigensolutions or line solutions that look like this. Except here, these things are, so here's the origin in both cases. Here, now, because mu is greater than 0, I have motion away from the origin indicated along these line solutions. For the clockwise twist source now, what is this going to look like? There's one emanating from the origin. There's another. Maybe here's another. And here's one more. And then lastly, right, emanating away from the origin in a counterclockwise fashion. This is what I have. Right, and here, this is going away from the origin. This is also going away from the origin. So this is a clockwise twist source. And this is a counterclockwise twist source. Okay. And so there's the last 6 cases that we hadn't talked about yet. So that you have 2 real eigenvalues, there are 5 subcases. You have 2 complex eigenvalues, there are 6 subcases. You have 1 real double eigenvalue. Those split into 2 like cases that are so one is when the matrix is a scalar multiple of the identity. The other is when it's not. So in the case of scalar multiple identity, you get 3 cases. Okay, in the case of not being scalar multiple of the identity, you get 6 cases. So altogether, that is 20 total cases that are possible here. Okay. Now, we saw that a lot of these are essentially repeated because the difference between them is that one's a source and one's a sink, or one's clockwise and one's counterclockwise. So the differences aren't always extreme, but technically they are different. And so these are 20 total cases. All right. Okay. So there is a nice list. So very nice list. A very nice list of all 20 cases on page 16 of chapter 3, section 7. So please have a look at that. You do not need to memorize this entire list, but this is kind of a nice. Actually, page 16 and 17 kind of give a nice. Page 16 and 17 give a nice accounting of all of these things. You don't need to think about like memorizing those in like a kind of like a systematic way or anything. But this nevertheless is a really nice kind of one-stop shop for everything you need to list out at least the names of those things. If you want to actually look at the pictures, you'll have to look at the specific examples. There's also mentioned in this section the mean discriminant plane. I'm not going to mention that here. I'm not going to spend any time on it. So the mean discriminant plane, this is something that is done on the very next page, on page 18. This is a very nice way of basically characterizing or categorizing or classifying all of the phase plane portraits in a single picture. Okay, and the picture is it's a picture of a plane with a parabola graphed on it, and basically regions in that picture tell you the cases that you're in. Okay, and so this is a nice way to visualize the classification of phase plane portraits for these systems. Okay, this is like a really, really nice way of looking at these things. But again, since you all don't need to worry about being too efficient in terms of how to remember all these cases, this is kind of just a curiosity for us. It's a nice form for the thing to take, but it's not going to be necessary for what we do later. So now I want to use this classification. This classification that we've done, breaking it into these 20 cases, to classify the dynamical stability of the origin. Okay, remember in each of these cases, the point that these pictures were centered around was the origin. Now we'll see here in a little bit where this comes into play regarding more general things. So we'll see where this comes into play regarding systems that are like nonlinear even. We're going to talk about autonomous systems, which includes the case of nonlinear systems, and we'll see where this talking about the origin comes into play there. But for us, it was the origin was always a stationary solution, right? It was our guaranteed trivial solution to these systems, and so you know, we can characterize all of these previous pictures. For instance, I'm just going to bring back the last ones as a question of stability of the origin in the same way that we did back in chapter 1 when we talked about stability of stationary points or equilibrium points for autonomous equations, right? So for our autonomous equations, we had this question. So if these were autonomous first order equations, we had this question of classifying stability of the stationary points. So I would ask you a question like, you know, is the following stationary point for this autonomous equation, is this, is this stable? Is it unstable? Is it semi-stable, right? Those are questions we could ask. I want to ask those same questions now, except for these systems. So, for instance, right, the question of stability before, right, so in chapter 1, we had a phase line rather than a phase plane portrait. And if we had, say, multiple stationary points, maybe this is what they look like. If we actually drew these in, and you'd look at these things and you'd say, okay, well, something like this we called unstable. and something like this we called stable, and something like this we called semi-stable, right? Or we just didn't care or didn't even give it a name because we didn't care that much about it. Really, we cared about unstable and stable. And remember, my justification for this, or for why we would care about this, was something that was unstable, took points nearby. So if you chose initial values that were nearby, no matter how close they were to this point, this stationary point that's not moving, no matter how close they were being pushed away. As t goes to infinity, they're being pushed away, pushed away, pushed away. That's why it's unstable. No matter how close I get to this thing, I'm being pushed away. Stable's the opposite. When I'm close, of course I'm being pushed towards, but even when I'm out here far away, I'm being pushed towards, right? But really the most important thing is when I'm in here close by, well, I'm getting pushed immediately towards this stationary point. So this is unstable, this is stable. This is semi-stable because it's stable on one side. So if I'm on one side, I'm getting pushed towards. But if I'm very close to it, even, on the other side, I'm still getting pushed away. So that's why it's semi-stable. Okay. Now we're going to introduce, so in our pictures here, you might notice something else. Well, rather than having a picture of a line like this, we have a picture of a plane. So we have more directions to consider. Okay, so for instance, let's look here. If I am at some point near the origin, notice I'm being pushed towards the origin along every trajectory. Right? So this should be an example of being stable. Okay. What about this thing? No matter where I am, I'm being pushed towards the origin, right? So if I'm somewhere near the origin, I get pushed towards the origin. Again, stable. This thing should be stable, both of these. Similarly, if I look at these things, if I'm near the origin here, no matter how close I am to the origin, I'm being pushed away along every trajectory, pushed away along every trajectory. So this should be the analog of unstable. Okay. Now, what we're doing here is that if we have stable, right, versus unstable, we're talking about points beginning near the origin. But as I said, if you notice, there's actually, in the case of chapter 1, the reason we didn't talk about this is because in chapter 1 there's almost no directions here, right? So there's almost no directions. There's only this single line of directions. But for us in the plane, there's more directions to consider, so this is a finer question. Okay, the question of whether or not you're stable or unstable, or what that means in terms of these pictures, because there's going to be stronger conditions we can talk about. So for instance, just to remind you, so this is going to be the same definition as before. So we say the origin 0, 0 is stable if every solution that starts sufficiently near it will stay arbitrarily close to it. Okay. It's unstable if this is false. So unstability is just determined as stability not holding. Okay. But now we have stronger terms to introduce that were basically identical to these terms in the chapter 1 case. But now we are able to ask a more specific question. We say that 0, 0 is attracting. This is attracting if every solution that starts near it will approach it as t goes to infinity. We say it is repelling if every solution that starts near it will move away from it. So near it but not at it. Okay. Now, a note here. Attracting implies repelling. Or sorry. That's definitely not true. Attracting implies stable. And repelling implies unstable. Okay. So attracting and repelling are stronger versions of stable and unstable. But let's see that they are different, right? So let's go back to what I've drawn here. So for instance, these are both examples of attracting, and these are both examples of repelling. But then what's an example of something that is, say, stable but not attracting? Right? So here, anything that starts near it is going to be pushed towards it as t goes to infinity. Well, what if I had something like this? It doesn't matter whether it's clockwise or counterclockwise. Let's say it's counterclockwise. Right. There. So it's a center. Notice if I pick any point near it, that point is just going to orbit around it like this. So this is stable, but not attracting. Why is it not attracting? Because it's not moving in towards the origin. So if I pick a point here that's close, it's just going to orbit around it for all t. It's never going to go towards it. Again, if I pick another t that's very, very close to it, it's just going to orbit around it. It's not going to actually go towards it. So it's not attracting. Here, anything nearby this origin gets pushed explicitly toward the origin. But that's not the case here. This thing just goes around and around and around, okay? Even if it's getting very, very close to it, I can pick one that's very, very close to it, but then it just stays at this in this elliptical orbit around it, okay? All right. So then what about something that's unstable but not repelling? Well, here's an example. What if I have a saddle? So here's my origin. And I have saddle where it's going towards it along one direction and away from it along the other. So this picture looks like this. And there's my picture. Notice, what is this? This is unstable. And it's unstable because it's not stable. So that means if I pick a point, say here, nearby, yes, it is being pushed towards the origin. But if I pick a point here, it's being pushed away. So not every point is remaining arbitrarily close. I could pick this point, and as t goes to infinity, it's pushed out and out and out and out this line. Doesn't remain arbitrarily close. That has to be true for every point nearby it. So this is definitely unstable. To see that it is not repelling, well, pick a point here. That actually gets pushed towards the origin as t goes to 0. It should be being pushed away. Some points get pushed away, but not all of them, right? This line, so things along this line solution get pushed towards it. So this is unstable but not repelling. So now you see that because we have more room here, we have a plane instead of just a phase line, we have more nuanced understanding of how this behavior goes. And that's why we introduce these two new terms of attracting and repelling that are not the same as stable and unstable. Okay, they're stronger terms than stable and unstable. So then this allows me to classify all of these things. So classifying stability of each case. So there's a nice table. This is on page 20 in the notes in this section. But we can draw this, or we can list this table pretty easily. So in the first column, we have attracting, so also stable. In the second column, we have stable, but not attracting. So remember, everything in the first column is also stable. Then we have unstable, but not repelling. And then we have repelling, so also unstable. Okay. So let's see what things are attracting. Well, the sinks. Nodal sinks, radial sinks. Doesn't matter whether they're clockwise or counterclockwise. Twist sinks. Spiral sinks. Okay. Now, there are some sinks that are not attracting. Right? But what are the stable but not attracting? Centers? Well, we already saw that in this picture, right? So centers are stable but not attracting. Spiral sinks, or sorry, not spiral sinks, spinal. Spinal sinks are stable but not attractive. And the null picture, the null portrait is stable but not attractive. Remember, in the null picture, nothing is moving, right? So yes, it's stable. If you pick a point nearby the origin, you are going to remain nearby the origin because every point you pick is a stationary point. So every point you pick remains exactly where it is for all time. Okay. All right, what about unstable here but not repelling? Well, there's saddles. Okay, spinal sources. And shears. Well, we have a picture of shears. Why is this unstable? Well, because it's not stable, right? If I pick a point here, it's being sheared this way. If I pick a point here, it's being sheared that way. So it is being sheared away from the origin, right? But not every point is sheared away, right? In fact, if I pick a point here nearby, it remains nearby. Okay, it's not being sheared at all. This is just a constant thing. So this is a line of stationary points. This is a line of stationary points. So this, a point here, is not being sheared at all. It's remaining stationary. So this is unstable, but it's not repelling because of that line of fixed points. Okay. Repelling, so also unstable. So these are the sources that you got from over here. So nodal sources, radial sources, twist sources, and spiral sources. So you'll notice the symmetry here in this table. Okay, the kind of sort of symmetry that's going on here. Now before you complain and say, wait, you said there's 20 total cases, but when I count in this table I don't get 20. Well, remember, a lot of these have, like spiral sinks, there's two different types, right? There's clockwise and counterclockwise. And spiral sources, there's clockwise and counterclockwise. So because of that, you should just be aware that that some of these have multiple cases from them. In total, if you sum up all of those subcases, you get 20. Okay. All right. So let's do a couple of examples here. All right. So maybe here's one. So let's say A has eigenpairs, let's say -1, 2, 1, and -3, -1, 4. Oh, why did I do that? Okay, so sketch face plane portrait, and classify stability of the origin. So I automatically know what general solution looks like, right? General solution looks like C1 e to the minus t times 2, 1 plus C2 e to the minus 3t times -1, 4. What do these trajectories look like? So I have two line solutions, right, from each of these terms. One's determined by the vector 2, 1, so that's this line. Okay, so if this is V1, this is the line CV1, or yeah, I mean I can call it C1, V1, whatever. And if this is V2, then this is the line D V2, right, if you like. Okay, so there's my two lines. Of course, the eigenvalues are negative along both, and so what do I get? I get motion towards the origin along both. Okay. So that's what the line solution picture looks like. Now, what case am I in here? Right, going back to all my earlier pictures. What case is this? Well, this is the case of a nodal sink. Right, so this is a nodal sink. So if I wanted to draw a few more trajectories, right, these would go towards, so here it would be going towards origin, like that. Here's another one. Here's another one. And here's one more. So this is a nodal sink, right? And this is because both of my eigenvalues are negative. Okay, now if I look at this picture here, nodal sink is in the category of attracting, so also stable. So 0, 0 is attracting and thus stable. I want to say both of these, whether it's attracting, stable, repelling, unstable, stable, not attracting, unstable, not repelling. I want to say all those things. Okay. So that's how this goes. Now, of course, you know, I now have the means to answer this for any sort of problem, right? If I have, well, let's just do an example of complex. Let's do an example of complex eigenpair. So let's do the exact same thing. Okay, for so let's do the exact same thing for eigenpair that looks like a -1 plus 2i with eigenvector 2i1. Now this is enough to tell me the other eigenpair, but I'm just going to write it anyway. This is -1 minus 2i, and then I can just negate this first term. I can just take the conjugate, so this is minus 2i1 here, and I need to actually know what the matrix A is, right? Why? Well, I need to know what A is because ultimately I need to answer the question of whether or not this is clockwise or counterclockwise rotation, and that comes from actually knowing something about the entries of A. Okay, and so this is mu plus, you know, my eigenvalues lambda are mu plus or minus I nu. Okay, so here, of course, mu is -1, which is negative. Okay, so then how does that impact the cases? Well, this puts me in the case of a spiral sink already, just knowing that mu is negative. So now I need to know whether this is clockwise or counterclockwise. And I figured that out by looking at A21, right? So A21 is equal to 1, that is positive. Remember the right-hand rule? Positive A21 indicates counterclockwise. And so what is the phase plane portrait for this thing? It is a counterclockwise spiral sink. So there is the origin. Counterclockwise spiral sink goes into the origin like this. Right, so there we go. Right, and so then this is coming into the origin like this. So again, this turns out to be a sink. So this is, we can just pull up our list here. Spiral sinks are attracting, so also stable, so this is attracting, and thus stable. Okay, so that's how we answer questions like this. Right now, you know, maybe as part of this problem, I'm asked to actually write out the general solution, so I can do that too. Of course, once I have an eigenpair, I can do that immediately. That's eigenmethod stuff, right? So that's exactly what we've spent the majority of our time doing in this chapter. Okay? All right, and so that's how addressing these problems go. Okay? All right, so let's move along. So the first thing I want to do is talk about something that's slightly more general. Okay, so now I want to generalize. I can't generalize completely, but the idea here is for the remainder of the course, I want to study what are called autonomous planar systems. Okay, so for the remainder of the course, I want to study autonomous planar systems which have normal form dx dt is equal to f of xy, and dy dt is equal to g of xy. Okay. Now, autonomous is exactly like autonomous for first order equations. Autonomous, of course, means self-governing, right? You think of it like the autonomous region of whatever country, right? It means that it is self-governing to some extent. So autonomous comes from the Greek meaning self-government. What does that mean in the context of this problem? Well, the reason why these are considered to be self-governing is that they don't depend on t. Now, of course, as before, right, you could say, wait, well, x and y are both functions of t, so of course they still depend on t. That's true. But algebraically, you can write these as only depending on x and y, and never just a floating, t variable showing up. Okay, so the only way that t shows up is as the argument for x or y. It doesn't show up otherwise. Okay, so this exactly mimics our terminology for autonomous equations back in chapter 1. Okay, so it is true that so a solution to such a system, is again a trajectory or orbit x of t, y of t, tracing out a curve in the planes, right? So these are tracing out curves in the plane. Okay, so each curve is thought of as an orbit or trajectory of the system. Okay. Well, it's actually true that it is still true. By existence and uniqueness, that each point in the plane has exactly one orbit passing through it. I should say it like that. Okay, so each point in the plane has exactly one orbit passing through it. So we get this nice idea of these trajectories, not being able to cross or touch in the exact same way that we did for linear systems. Okay. All right. Now, it turns out that understanding what it is that's going on here requires us to understand stationary points of the system and what are called semi-stationary points, which are a thing that didn't show up in chapter 1 because, again, we were one dimension less. And so we are close. We are very close to recasting this in a way that's going to make the connection to chapter 1 stuff a lot more obvious. Okay. And so what's the main thing that I want to say here? Well, first, let me mention what to do in order to find stationary solutions. So maybe it makes sense to actually define stationary solutions first. So definition. a stationary solution to dxt equals f of xy, dyt equals g of xy. Does not depend on time. I.e., it satisfies the equations f of xy is equal to 0 and 0 is equal to g of xy. Well, this is just the fact that it doesn't depend on t means the left-hand side of both of these things is 0. And so this is what it satisfies. Okay, so this is an algebraic system of equations. Okay, so another way to say this is if the point x naught y naught satisfies f of x naught y naught is equal to 0 and g of x naught y naught is equal to 0, then the trajectory x of t, y of t, just defined to be that point, is a stationary solution to star. Okay. So this goes in both ways. And so what that means is that I can find stationary solutions by just solving this. Okay, so solving this yields stationary solutions. So let's see an example of this. Okay, so find all stationary solutions to the following. So find all stationary solutions to the system dx dt is equal to y and dy dt is equal to 4x minus x cubed. Okay. Well, I've already shown here that, by definition, stationary solution has to satisfy this algebraic equation, so it has to satisfy the algebraic equation 0 equals y and 0 is equal to 4x minus x cubed. Okay. Now, this y equals 0 is one thing, okay, but this has multiple solutions, so I can rewrite this as x times, factoring again, this is like 2 minus x, 2 plus x. Alright, and so x is equal to 0, or x is equal to 2, or x is equal to minus 2. Those are the three things I get here. Y always has to be 0 from this. So what stationary solutions do I get? Stationary solutions are 0, 0, 2, 0, and minus 2, 0. There they are. Okay. So I've got three stationary solutions, three different points. Okay. Let's do another example. So find all stationary solutions to the system dx dt is equal to y plus 9 minus x squared, and dy dt is equal to 2xy. Okay. Alright, so what are these things? Well, stationary solutions would satisfy 0 equals y plus 9 minus x squared, and 0 equals 2xy. Because, so here's how these go, right? And you might remember this from Calc 3 a little bit. when you have an algebraic system of equations, when the equations involved are not linear, right? So when they're linear equations, then you know how solving them works. This is Gaussian elimination or, linear algebra stuff, right? Row reduction. So that's what makes the linear case so nice, is that there is a systematic way of going about solving this. Now, when the equations involved are nonlinear, so when both of them are like polynomials or involve sine and cosine or whatever thing, there is no systematic way of doing it. You just have to look at the equations and ask yourself, like, what can I use here, right? So in this case, here, 2 times x times y is equal to 0. That puts a pretty hefty restriction on x and y. This means that either x or y is 0, right? Maybe both of them could be 0, but one of them has to be 0 at least, right? So we take the second thing and we say this implies x equals 0 or y equals 0. And that might require us to travel down some paths. Now, if x is equal to 0, then y plus 9, so this takes us down the path that y plus 9 has to be 0, so plug in 0 here to this second equation. Y plus 9 0 implies that y is minus 9. Okay, so if these two things are going to satisfy this simultaneously, y has to be minus 9 here. So both x and y being 0, while that would satisfy this equation, it's not going to satisfy this one. Right? 9 is not equal to 0. So y is equal to minus 9. Okay, let's trace through the possibilities if y is equal to 0. So if y is equal to 0, this means that 0 is equal to 9 minus x squared, which means that x is equal to plus or minus 3. So how many stationary solutions do I get? Again, I get 3. So what are my stationary solutions here? Stationary solutions are 0 minus 9, 3, 0, and minus 3, 0. Okay. Let's do this again. Maybe I'll do it on a new sheet. So find all stationary points. Of the system. Dx dt is y minus x times x minus 1, and dy dt is 3 plus 2x minus x squared times y. Okay, so we know that stationary solutions have to satisfy the following, right? They have to satisfy the equation 0 equals y minus x times x minus 1. And 0 is equal to 3 plus 2x minus x squared times y. Now, again, we are dealing with a nonlinear thing. Okay, when you're dealing with a nonlinear thing, there is no systematic way of going about solving these things. You just have to look and see what you can do with maybe the equation that's simplest or at least gives you the most info. So I'm just going to pick this first equation for now. What does this tell me? This tells me that one of these has to be 0, which would mean that y is equal to x or x is equal to 1. Those are the two possibilities I get from this product, a times b being 0, right? So either y minus x is 0 or x minus 1 is 0. Each of those things respectively means y equals x or x equals 1. So now I have to follow each of these things. Okay, let's follow the x equals 1 thread. If x is equal to 1, then 0 is equal to 3 plus 2 minus 1 times y. So 3 plus 2 minus 1 times y. What is that? That doesn't really matter because this is equal to 0. So this is 4y is equal to 0, which implies that y is equal to 0. Okay. So y is equal to 0 here. All right. Now, what about the y equals x possibility? So if y is equal to x, I plug that in here. So this means y equals x means that 0 is equal to 3 plus 2x minus x squared times x. Okay, but this factors, right? This factors as 3 minus x times 1 plus x times x. So the possibilities there are x equals 3 or x equals minus 1 or x equals 0. Well, in each case, y is equal to x. So that gives me 3 points each. So in total, I have 4 points. So from the first, I have, so what are my stationary solutions? Well, I have 1, 0. And then I have 3, 3. And minus 1, minus 1. And 0, 0. Okay. All right. Now, in each of these cases, in each of these examples we did, we had finite number of stationary points, but there's no reason that has to be the case. If one of these equations had involved like sine or cosine, you can easily see how, well, you know that sine and cosine have infinitely many zeros, so you can see how infinitely many points as stationary solutions might arise there. In fact, there's an example. In your textbook, this is chapter 3, section 8, page 4 has an example like this. Okay. All right. So now I wanted to address one other thing that can happen for these systems but can't happen in the earlier case of autonomous equations or for single equations. Back when we were doing this in chapter 1, this didn't make any sense because we didn't have as many variables showing up, right? We didn't have an x and a y. We only had an x or a y. We only had one of them. Okay, and so what is a stationary solution? So then, a semi-stationary solution. So what are semi-stationary solutions? This is one of the unknowns, x or y, does not vary with respect to t. Okay. Well, how do I find this, right? So a semi-stationary solution of the form a y of t, okay, will satisfy the equation dy dt is equal to g of ay. Right, where a is some, right, x equals a is a constant. Okay. It will be of the form, so a semi-stationary solution of the form x of t b will satisfy dx dt is equal to f of xb. What are these, though? What are these equations? These are autonomous first order equations. I.e., we did this in chapter 1. So the autonomous first order equation analysis we did back in chapter 1, we'll do it. Okay. Okay. Well, let's look at some examples of how this works. So, example. What about dx dt is equal to y and dy dt is equal to 4x minus x cubed? So we just had a look at this. Well, there is no value of x that makes the right-hand side of dx dt equation equal to 0. So there is no value of x that makes this thing equal to 0. There is no value of y that makes the right-hand side of this thing 0. So this has no semi-stationary solutions. Okay. All right, let's do one more example. Okay, let's do one more example. So let's do this second system we looked at. So dx dt is equal to y plus 9 minus x squared, and dy dt is equal to 2xy. So what are the semi-stationary solutions? Okay, well, when y equals 0, right, the right-hand side of the dy dt equation is 0. Right, so when y the right-hand side here equals 0 for all x, right? When y equals 0 and when y equals 0, this thing, we get the right-hand side of this becomes dx dt is equal to 9 minus x squared, which I can factor as 3 minus x, 3 plus x. Okay. What is the solution to this at some initial value x naught when t is equal to 0? So the solution to this autonomous equation, we can do this with chapter 1 stuff. The solution to this for initial value x naught at t equals 0 is what? This is x of t is equal to, remember what we did for autonomous equations here, in this one we can go ahead and say this is equal to 3 times 3 plus x naught e to the minus 6t minus 3 minus x naught over 3 plus x naught e to the minus 6t plus 3 minus x naught. Okay. So this system has semi-stationary solutions that look like what? Thus. Thus, this system has semi-stationary solutions that look like the following. So x in the first slot is this thing, 3 times 3 plus x naught e to the minus 6t minus 3 minus x naught over 3 plus x naught e to the minus 6t plus 3 minus x naught. And 0 in the second slot, right? Because this is for y equals 0. So this is what the semi-stationary solutions look like. Okay, now you might say, well, semi-stationary solutions, stationary solutions should also be semi-stationary, so somehow I should be able to recover stationary solutions from this. Well, notice if x naught equals 3, x naught equals minus 3, we recover the stationary solutions. Minus 3, 0, and 3, 0. So 3, 0, and minus 3, 0. Okay. But one of the stationary points is not included. Okay, so 0 minus 9 is not included in these semi-stationary solutions. Okay. Now, if you're confused about how we actually got this solution, go back to Chapter 1, Autonomous Equations, and solve this right, using the methods that we used. Okay. You can solve this. Remember, an autonomous equation is a special case of a separable equation. Okay. All right. So this kind of prepares you for what is coming next. Once you see that these things are kind of tied very closely to what we did back in Chapter 1. So it is clear. Note, every solution to star satisfies the following. So let me just remind you what star is. Star is this system. dx dt is equal to f of xy, dy dt is g of xy. Okay. Well, what is minus g of xy times dx dt plus f of xy times dy dt? Well, by this fact, dx dt is f of xy. So this is minus gxy times f of xy plus f of xy times dy dt is g of xy. And so minus gxy fxy plus fxy gxy, this is 0. Clearing denominators, right? Again, abusing notation, treating dx dt and dy dt as honest to God fractions here when really we know they're not. Clearing denominators here, I get minus g xy dx plus f of xy dy is equal to 0. Oh. Huh. Huh. What is this? This is called the orbit equation for star. And I want you to notice something, right? You've seen this before. This is very similar to the differential form for these exact differential form questions back in chapter 1. In fact, in regions where f of xy is not 0, I can rewrite this as dy dx is equal to g of xy over f of xy. So I can recast this equation as this thing. And in regions where g is not 0, I could recast this as dx dy is equal to f over g. This is another way of recasting these two equations. Right? So this describes a relationship between x and y here that brings us back to chapter 1 stuff. Okay, so we'll see a little bit about how this goes in tomorrow's lecture, and we'll see that what we're doing or what we're about to do is the notion of integral methods for these systems, okay? Which means we're going to try to explicitly find solutions to these systems. Now, we're going to see that a lot of times this can't be done, and we'll have some methods that we apply when we can't do that, but this is really going to let us say some really nice things about what is going on here, and it's going to let us draw some really nice pictures to see what is actually happening for these systems. So we are almost at the end, where the culmination of all of our work. We're going to be able to apply all this stuff and get some really nice pictures out of these systems. But anyway, that's all I have to say for now. Be looking here in a little bit. I'm about to post your last midterm, so before the final exam. So anyway, I'll make an announcement when I do that. But until tomorrow, I will see you later.